So it's a pleasure to be here. Thank you for the invitation. And it's really a wonderful place for thinking and discussing. So this work that I will present is revisiting the proof we had done with Cédric Villani and obtaining new results, in particular about the critical regularity we had conjectured. Actually, we didn't prove it's critical, but we reached it at least in Gevrey spaces. And what I like most about the new proof is that it's arguably shorter, but it contains a lot of tools that themselves, if you would really expand them, makes the proof not so short, but it's certainly much more flexible, much more robust, and much more in the language of dispersive or wave equations. So I hope it will be helpful for further studies in this area. And this, so how did this work started? Because I was interacting a lot with Nader Masmoudi and Jacob Bedrossian when they were working on a paper they just preprinted not so long ago about Euler 2D. This work of them was strongly inspired by our work with Cédric, but for this work it turned out that they had to develop other viewpoints, and then that was the starting point. We wanted to see whether these other viewpoints could be useful as well for Vlasov. So in a couple of minutes, let me just write the model and just say in a few words why it's considered the fundamental equation. So the so-called Vlasov equation is as often not first written by Vlasov, but by Jean. So the name is not exactly correct. First in the context of galactic dynamics, and then by Vlasov in the context of plasma dynamics. And the origin of the equation is extremely simple. If you just write the Newton equation, so let me try to keep a convention, a sign convention correct along the talk. Right, so you write Newton equations, let's say, among indistinguishable point particles with mass 1. And you can write the Liouville equation for this joint particle density Fn, corresponding to the Hamiltonian of this system. Another object you can write, which is quite well known, is the so-called empirical measure. X to the n means all the positions of all the n particles. So you're sampling positions of your particle in the phase space of position and velocity. And you can check formally that there is an equation for this empirical measure, which is now it's a little v, corresponding to the variable of the measure itself. And okay, so that's it. And so if you can pass to the limit to some object, then you expect the limiting object to satisfy this nonlinear mean field equation. There's actually an equivalent statement, which is to say that the first marginal of my n particle distribution would converge to an object which happens to be the same. These are called chaos properties. But anyway, it has been proved, and there's a bunch of very nice results by Braun, Epp, Dobrushin in the late 70s, early 80s, that proves that for smooth interactions. Unfortunately, for smooth W, which is on the left, unfortunately, it's open for the interaction I will consider for Coulomb and Newton. And that's an important open problem, which is a bit frustrating in this field, even for short time. Okay, so and the system that I will consider here, on which I will establish some kind of global in time estimates, is the following. So The unknown is a scalar quantity, just one scalar quantity depending on position velocity, which has to be interpreted as a probability distribution, and it satisfies this nonlinear equation. There's a force field here, which is given by this. So I have to pick up one framework, right, to do the study. So I consider the periodic case. Let me explain. So the variable x lives in a torus with size L. Which is not very physical, but I mean, that's what we can do for the moment. That's one of the open problems, to go to something better than that as a confinement. V lives in Rd. So this has exactly the form of a Liouville equation, apart from the fact that the force depends non-linearly on the solution F through this rho index F, which just means integrating partially in the velocity variable. So it produces a function depending on x and v, and x and t. So this term here allows for having global neutrality, and you can check that then the constant in your torus, the solutions which are constant in space in your torus, produce cancel the force. So you can produce very easily a lot of stationary states like that. This term is perfectly well understood in plasma physics. It corresponds to the background of ions that ensure global neutrality. In gravitation, it's a debate, a very interesting debate in theoretical physics, which is beyond my skills in theoretical physics. It's the so-called gene swindle. But it is used as well. The justification is not so clear. Swindle. Is it? Yeah, I mean. Cheat, right? Sorry? Cheating. Yes, cheating. Yes. Yeah, well, initially it's cheating because we don't know how to do anything mathematically without, but it has also been justified by some arguments. Well, that's a bit different from what I want to talk here.
I'm not sure I understood the word. Just on your first equations there.
Yes.
I mean, if what you mean by that Poisson brackets.
Yes.
Then it should be Fn Hn,
yes.
not Hn F.
Okay. Sorry. I simply cannot remember these things. It does not. I cannot wire these things in my brain. Yes, right. So, okay. So then the main phenomenon I want to study mathematically is very easily explained. So the Landau damping, the name is given because of the paper of Landau. Actually, to be completely fair, Vlasov made also interesting remarks related to this effect in the 30s. And the idea is to prove the decay of spatial oscillations of the spatial density, and then, as a consequence, of as well the force. So the equation is reversible, but we want to prove some irreversible decay only on some average of the solution. So that was the original idea, and this is very well observed experimentally. And the paper of Landau does a linearized analysis, which has been justified by many mathematical work. But the first nonlinear justification was done. So the first step was done by Cagliotti and Maffei in the 90s, and then Wang and Velasquez in 2009, they proved the existence of globally in time of solutions that satisfies that. And the Cauchy problem for the nonlinear equation, so saying there is a neighborhood that for which all solutions will satisfy this, was done in the paper with Cédric, published in 2011. So there are lots of other works. I mentioned only the results mathematically related to the nonlinear solutions. To finish with the model, the cases we want to consider are two kinds. So for the potential, we want to consider either the, let me put B for background, either the plasma case, where there is the charge E, or the gravitational case, where there is the mass and the gravitation constant, where here you remove an average. This is the Jean Swindle. And these two cases, of course, have opposite signs. So in this case, we consider repulsive interaction between the electrons and attractive interaction between stars in a galaxy. As a general remark, the stage of the mathematical theory at the moment is we don't know how to really use anything better in this case as compared to this one. I mean, that's a general problem for nonlinear Vlasov equation. This case should be more stable. For instance, you don't see collapse instability for this case. Okay, then we want to to reframe that as a nonlinear PD stability problem. This will be a perturbative study, of course. So we consider, well, let's normalize the size to pi. I will maybe mention at some part in the statements when the dependency in the size of the box is really interesting. And let's consider a fluctuation of a steady state of this form. So the steady state is of this form. It's f0. Let's put this 0 as an exponent of v. And observe that if it depends only on v, then you cancel the force, and you obviously cancel as well the transport and the time derivative. So you produce a stationary state. We want to study the stability problem for this H. Right, so since I will transform several times the equation, let me just write it once on H. Okay, where here by rho H, I mean as before, as you can guess, the integral of H in V. Okay, and you want to prescribe small initial data. In some topology that will be in this talk Gevrey, actually. And so we want to prove global in time estimates on this H. I will explain why in a second. Under some stability condition on F0 that were essentially identified in the paper, partially in the paper of Landau and mostly in the paper of famous paper of Penrose. So we will use this stability criterion in this physics paper that we reframed in a more estimate form to be used for estimates. And then we want to prove regularity on this H. The key point is that we reframe, and that was an idea in the paper with Cédric that we use here as well. We reframe the question of decay of the density in terms of proving uniform in time, I mean, regularity estimate on this H here in the moving frame. in the frame following. So following what exactly? So this is really reminiscent of a lot of results in so-called scattering theory. We want to use a frame that matches what we expect the equation to be asymptotically. And asymptotically, we will expect these two terms to disappear. So we expect the equation to be only the free transport. So we use the moving frame following the free transport. Okay, so we will completely now forget the initial question of Landau, which will be a consequence of the regularity estimates. So here is the main result. So it needs a few minutes to state, because I will have to explain the norms. The norms are much simpler than the one we used in the paper with Cedric, but still have to be written. So I define for a function h as above. Well, let's forget the time variable for the moment. Depending on x and v, I define a Gevrey space with Gevrey exponent lambda, Sobolev correction sigma, Gevrey exponent power, Gevrey power s as the following. So I sum over k, I integrate over eta, then I do everything in L2 based space. So I multiply by this Sobolev term and then an exponential term. Okay, so I have to explain a few notations that will be in this talk used all the times. So so you see the power of the Gevrey space is here. If you take S equals 1, you recover analytic regularity. Here I will consider S between 0 and 1. Actually, it turns out that my critical threshold for Coulomb-Newton will be 1/3, which is what we had conjectured with Cedric. And this is the Japanese bracket. So sometimes I will put with a comma several quantities, just meaning that I sum them, and each quantity means it's basically a weight of order 1, just modified a bit at 0 to avoid issues. Okay, so this is my norm when I have all the variables, and if I consider a function of x only, so think of it as my density rho, I will consider this strange looking norm at first sight, but you will see, I hope, in the analysis why it's completely natural. So k, as you see, is the Fourier variable of x, and eta is the Fourier variable of v. Right, and then 2 lambda k kt to the s. Okay, so you will see that again several times. What I'm doing here, I'm just taking a trace, if you want, for eta equals kt.
You don't put a 2 on the sigma.
Oh yes, you're right, actually. Okay, so rho depends only on x, but we project the weight on kkt. So k, the mode of rho. So there's a G norm, an F norm. So the G norm will act on functions of x and v, and the F norm will act on function of x only. Sorry? Ah, yes. This norm actually depends implicitly on the time. Yes.
The G norm, the line is I don't see any T. Where is the T?
The G. Yes, sorry. It's supposed to be calligraphic G and F. They have nothing to do with the solution or whatever. So, yeah, I mean, then it becomes very natural. You will see why. This norm in particular, if we can prove, let me keep track of a time also in tau to make it clearer. Right, so it's a Sobolev correction KKT, each of them, and Gevrey both in K and KT. Okay, you could say that for large T you could forget the K, but it's just much more clear the structure if I keep it, because you see that it's a projection of this norm.
So you have two norms going here, is that right?
Right, yes.
I can't quite distinguish them. So you had the first one, I see this circle. And the second one is kind of like how are they different?
Yes, okay, so let me come back to this. So one norm is really acting on function of both variables. And this is simply measuring Gevrey regularity plus some Sobolev correction in both frequencies. The other norm is acting on functions of x only, meant to be used for my averages in velocity. And it acts in a strange way. I just particularize the regularity multiplier here to KKT. The KT will really come from the moving frame, actually. It means when I will take my average, before taking my average, there will be the moving frame, and it will bring the regularity to KT. So that really measures how the energy is moving in Fourier space. And observe that, that's what I was going to say, the original question of Landau is recovered if you prove uniform bound on this. Because if you prove uniform bound on this norm for all time, then the KT weight is increasing and means that you get exponential decay on the rho. Well, not exponential here, stretch exponential when I'm in Gevrey. So that exactly reframed the decay into proving No, it's weaker. I really assume S between 1/3 and 1. Yeah, okay, so going to Gevrey is interesting because you can make local modifications, but the main goal here, we wanted to push as much as possible the analysis, and we reached this 1/3 that for the moment we cannot go beyond.
And the second moment, so it's not a norm on function of x and t, it's a t-dependent norm.
Yes.
Of x.
Yes, yes, yes.
So in your norm, there's really a lambda sigma s and t.
Yes, actually, we tried to make the notation slightly lighter than in a paper with Cédric because they were maybe a bit frightening, but to be fully correct, one should keep track of the t as well here. And
But then there's no t in the row there, right?
no, I'm not obliged to put one, but actually what I'm doing, I'm really using a regularity multiplier depending on time, but it turns out that in the analysis, I will always use the same time here and here. That was a major technical complications in the paper with Cédric. We had to use different times here and here, and now we can make the analysis. So you can forget a bit about that, thinking that my multiplier will always use the same time as the time of my function. Okay, so it's almost there for the result. It's a bit long, but so now I have to state the stability condition. So it's a refinement of the stability we had done with Cédric. So if I don't have enough time, I will probably skip the proof. So I put a weight in V. I will say later why we need weights in V. I'm supposing some Gevrey regularity on F with some, let's call it lambda F0 maybe. I don't need Sobolev correction because it will be higher than everything I use afterwards. Actually, the Gevrey will be analytic here. I use it with 1. So I have a bound on that. And then I define something which is well defined. If I have enough regularity weight, I define this quantity. So this comes out of a Fourier Laplace transform of kernel times profile that you will see later. So here I take Fourier of my profile at kt, W Fourier, which is my interaction. Okay, and I integrate this quantity. My W, I should have said that. My W from now on to make it, to forget about physical constants and so on, that will be just a kernel that satisfies in Fourier that is less than a constant times some decaying like -1 minus lambda and minus gammas. And the gamma equals 1 is the case I'm interested by, which is Coulomb and Newton. Okay, I just create a range of potential that can be nicer than Coulomb and Newton, just to see what is the critical case. And the condition is that it's like a dispersive relation, if you want, dispersion relation. I have a condition that this is bounded below when I take the infimum over all frequencies k, and when I take also for all real psi less than some lambda bar. So and the lambda bar is greater than 0. It's not the same as this one, be careful. So I ask that in a half plane, let me do a picture. There is no pole of this L minus 1. Okay, so there's a small subtlety here. I will use this lower bound in the whole strip here, in the estimates, but I really need that there is no pole in the whole half plane. Right? So I will explain that in a minute. So under this condition, the theorem is that, so you assume that F0 satisfies L, of course, with all the constants stated before. You assume that you have Gevrey. So in this talk, I will only explain the case different from analytic. With the same techniques, you could also do the analytic case, but there are a few twists in the proof. So S is between 1 and 2 plus gamma, and since gamma equals 1 is the Coulomb case, you recover this 1/3 threshold. And then you consider index of Gevrey regularity lambda 0 for initial, lambda prime, which is meant to be final, even if the name is not great. They don't have to be related to the regularity of F0 because it's analytic, whereas here is Gevrey, right? So any index here is dominated by the analyticity. And there is a stability, a size of stability epsilon 0, so that for all epsilon less than epsilon 0, and H initial such that you have this bound in this Gevrey topology with this lambda 0. So we don't need Sobolev correction at that point. Then we have all the things we want. There will exist a global in time solution. The existence of global in time solution in general is known for this equation. That's not the main point here. So there is an existence of global solution F T, which writes as my stationary state plus HT, where and some target scattering, let's call it like this, H infinity, which also belongs to a Gevrey space like this, and which is actually close in that space to my profile. Oh, so it's for h, so close to 0. And then I have the following estimates. H x plus vt v minus h infinity xv. This measure in Gevrey regularity is controlled by epsilon and just epsilon for this one. It's uniform, and the second estimate is that rho of t in, let's keep the 0 as well here. The rho t here is controlled in this projected Gevrey regularity by epsilon and some exponentially decaying term. Well, that's what comes out of the proof, but I mean, important thing is that it's exponentially decaying. Okay, so yeah.
Roughly speaking, there's some kind of scattering in momentum space, is that right, in velocity?
So what's happening?
You're
Yeah.
going to approach one of the equilibrium, but you're not going to approach the usual one. You're going to approach a new, sort of a normalized one.
Yes.
It comes out because of some loss of mass at infinity.
Actually, there's also loss of mass at infinity. The key point is that it's weak convergence for the initial frame.
Yes.
Because there are there are oscillations on the momentum variable that the amplitude of oscillation goes to infinity a long time, of course, if you stay in the original frame. So you could say there is some kind of convergence, but weakly, right? And actually, if you want to understand the convergence in some strong norm like that, you change the frame. So there's actually also convergence to that. Actually, you could also put some exponentially decaying term here.
What is H infinity?
Yes, so H infinity is a target profile that you understand once you mod out the free streaming, right? So the equation does converge to something because of the fact that, well, that's the nice aspect in this nonlinear equation. Because of the phase mixing, so that's usually the name used in physics, due to the free streaming, it induces some decay on the force, the two force terms that are here. And because they decay fast enough, they induce then some asymptotic convergence once you properly mod out the free streaming.
You don't expect H infinity to be 0. It's not going to be.
No.
It's going to depend on X.
But in the original frame, it goes to 0. So the H infinity has average 0.
The H infinity will have global average 0 as well, yes, because we start with a 0 mean fluctuation and it's conserved.
The original variables, things will go to 0.
Yes, you're right, actually, yes. It will be a 0 for the weak convergence, yes. But actually, in general, it's, for your question, Joel, it's hard to predict what it is. It's really produced by the whole memory of the evolution, the nonlinear evolution in time. If you
It will depend on X.
It will depend on both X and V, yes. And if you solve the linear problem like Landau and Penrose did, it's much simpler. You can really easily see what should be this profile, but in the nonlinear case, it comes out of the nonlinear evolution. That means to me.
Let me ask you about the linear case first. So
Yes.
where it comes out of it. So then in that case, does it come from some kind of zero in the linearization, some kind of zero mode, or what?
Yes, exactly. That's exactly that. The 0 mod in X. That's exactly what it is. So you know what it is because it's the velocity distribution itself once you take the 0 mod in X. But it's because the linear equation, in the linear equation, well, I will definitely not have time to prove the stability criterion, but the core idea here is that for the purely linearized equation, the spatial modes do not speak to each other. You have separate closed equation on each spatial mode. And
So this one is not a condition. If you can prove it,
so this condition,
this one,
yes.
this you can prove it, or this is a condition
No, this is a condition. You assume that on your profile. If you have that, it in particular, it is implied by the so-called Penrose criterion. So, well, it's a long stuff, but let's say, for instance, the Gaussian satisfies that, the Gaussians in velocity. Any purely monotonic profile will satisfy that. That was the motivation of the paper of Penrose. Once you have that, you observe the damping for the linearized equation. That is an elaboration of the argument of Landau, basically. And this is based on Fourier Laplace. And, but for the linearized equation, it's very easy to predict what is this asymptotic state. For the nonlinear equation, of course, we don't compute it. We just obtain it as a global in time integral in time of the action of the nonlinear terms.
Actually, Penrose is Albert Penrose.
Yes, it's the brother, right? Yeah.
The one I worked with.
So, okay, maybe let me continue some comments on this. So it's a kind of scattering result, really. It really means that the equation is asymptotically scattering.
F0 will not change. I mean, in the problem, your F0 stays fixed from the beginning to the end. It will not change.
Yes.
Yeah, but in lots of nonlinear Schrodinger equation problems,
Yeah.
you sort of can change.
Yes. No, you're right. So, yeah, okay, let me say something on that. Actually, here, this is the first result of this kind for Vlasov equation, and it's very limited, clearly, because we identified a subset of stationary solutions that are so simple that we really say if we are close to that one, we will remain close to that one and go weakly to something homogeneous. But what we really would like to consider are BGK modes, for instance, for plasma, things which are space-dependent, periodic, and so on. Or if you consider Euler, we would like to consider, well, a lot of things. Even the vortex, actually, solution is not well understood. The work of Bedrossian and Masmoudi is for the simpler linear shear flow. So we are far from that. Here we can make things work because we have this very simple class of stationary solution, actually. What else? Yes, the size of stability degenerate when the size of the domain goes to infinity in this analysis. That's important to notice. So that's an interesting open question on which we are thinking about to prove a kind of damping result, of course, not with such strong time decay in the whole space. Yes, so it measures really Gevrey regularity, and even improves with time. And another thing is that there is a similar result, of course, for time going to minus infinity, but for a possibly different profile. We had checked that actually they are different in many situations. And out of this analysis, so one very natural question is this regularity critical? We have no proof that it is critical. It's critical in the way we do the proof. For instance, we would like to have a result with Sobolev regularity for the fluctuation. That would be much more natural. It turns out that the key nonlinear instability mechanism that we have to control forces us to have Gevrey regularity for the moment.
The space F itself, if it's dominating that zone, then already encode the exponential decay.
Yes.
Because you have KT to S.
Yes.
But you claim that there is further exponential decay.
Yes, you're right. Actually, I think.
That's what you say now?
No, I think you're right. Now that I remember, well, you can still keep a little bit of it, but well, let's put some delta. We use in the end that you keep a little bit of it, but you're right. There's already some decay here. Here it's important to have some decay. It comes from estimating the time integral of accumulation of nonlinear effects starting at t up to infinity. So you really have some exponential decay.
Where does the dimension enter or doesn't enter?
So no, it does not enter. The damping effect is a one-dimensional effect, actually. So the dimension plays no role here. Well, of course, there could be other problems. You know, in 4, well, if you go to higher dimension, you could have problems solving the Vlasov-Poisson equation. But this perturbative argument is not sensitive to the dimension.
So why do you stay on a torus?
So exactly for that, that was exactly the question of HDAO. Actually, we want to have a very simple class of stationary states. Let me give an example. You want to consider, for instance, a plasma confined by a magnetic field. That will be much more natural. But then there is a very subtle interaction between the self-created field and the external field you impose. It's much harder to expect what will be the limiting scattering equation.
So you're telling me you're going to have some kind of confinement mechanism anyhow.
Yes.
So you might as well put it on torus. I mean, and it makes it easy for yourself.
No, actually that's a very deep point on which for the moment I have no idea how to make progress. Let me say it completely mathematically. We are in a case where we know what will be the limiting scattering equation. The limiting scattering equation will be free streaming. Right? It's like studying a perturbation of wave equation where you know that the scattering will be the linear wave equation. Of course, it helps a lot. So it's exactly similar to that situation. If you put a confinement which has some geometry, you cannot easily guess what will be the limiting scattering equation. And we need that guess to use the proper moving frame.
You can't figure that out as you're going along, right?
Sorry?
You might try to figure that out as you're going along.
Yes, so there's a little bit of it in the Euler 2D paper of Bedrossian and Masmoudi. There is a very interesting idea. They have to solve something which is a step in this direction, to update the moving frame a long time, yes.
If you start in RT, and then you make your H local, presumably everything will fly away and you will get...
Oh, okay, for repulsive, yes. But for gravitation, of course, there are cases where it maintains its coherence, which is also a beautiful question, but which, again, comes with this very, very deep geometrical difficulty.
But for the repulsive, can you show that or not?
Well, actually, for repulsive, there are lots of results giving you polynomial rate of decay on how it disperses in the whole space. What you could imagine would be to have an infinite mass, infinite energy solution that you perturb in the whole space. That's another thing.
Yeah, that you say you lose regularity. You have to do something as you make L bigger and bigger.
Well, for the moment, the way the method is done, the stability size here, this epsilon 0 is degenerating to 0 when you consider boxes larger and larger.
So could you just very quickly remind me of this result of Masmoudi
And Bedrossian. Okay, so they consider the Euler 2D equation, and to have a framework which looks close to the Landau damping for Vlasov, they consider that they put the, let's call it x variable in a periodic 1D, so in a circle, and the other variable in R. Okay, so this variable will play the role of my space variable in Vlasov. This variable will play the role of a velocity variable. I'm just making a parallel with this result. And this parallel had been noticed by already in physics paper, and then you consider a shear flow in this direction. And you want to prove that a perturbation of a shear flow with lots of Gevrey regularity will asymptotically again scatter towards a new shear flow. But the profile is not exactly the linear shear flow, slightly modified. So then it requires a bit of what you were asking for. It requires a bit of updating the moving frame better than that. But it actually modifies at a next order, so they can still make it work. But that's the typical result they prove. And that's called, in this context, that's called inviscid damping. So the mechanism is the same. You average in X by putting oscillations in Y. Just like here, we average in X by putting oscillations on the variable V. Okay, so I will try to detail the strategy of the proof. Maybe not the exact calculations, but and I mean, there are lots of situations where a similar mechanism could be studied. One, where certainly it plays a key role, is the stability of vortices like the Jupiter grid red spot, where, well, now it's not x, y, it would be radial angular variable that would play this role. That is not known. That's a beautiful question to look at. Or maybe in some Gross-Pitaevsky situation, reframed in Wigner, there is a similar structure. If you look at the Wigner equation corresponding, which I don't think has been studied in this, with this viewpoint. So strategy of the proof. Okay, so let me start at a general level, and I will try to go deeper and deeper into the technicality according to the time I have. So some of the same, there are ideas which are similar to what we had developed with Cédric, so let me list them. As I said, we reframe decay into a regularity problem, proving regularity estimates. A second important idea is to isolate two very different kind of terms in the PDE, which we called transport effects and reaction effects. So in our case, it meant transport effect was when rho was forcing the full distribution. Reaction effect was when the full distribution was forcing rho, roughly speaking. But here you will see it's completely reinterpreted in paraproduct formulation, which I found that's one of the nice things I found I find of using these paraproduct techniques. And then we need to isolate and control the echoes. Okay, so plasma echoes is a way the plasma keeps memory of interaction between spatial modes in a way, and it keeps too much memory of them in a way that could destabilize what we want to prove. Okay, then the new, the novelty of this method of proof of the following. The transport reaction structure is obtained by paraproduct. So I should have time. I will give a sort of very simple model kind of decomposition and inequality. The transport effect, they were treated in our paper with Cédric by Lagrangian method, and that was one of the reasons the proof was so long. We had to mix Lagrangian and Eulerian kind of estimates in the same norm. So here they are treated by energy method, making the proof more unified, using commutator estimates to take advantage of the cancellation of transport structures. Okay, that's and a third point, very important, is that there is a loss of regularity due to the echoes. That in our proof with Cédric, we were writing a quite heavy Newton scheme, and it was corresponding to loss of analytic regularity at each step of the scheme. Here we use a nice idea that was, well, actually that goes back to the proof of Cauchy-Kovalevskaya, but that has been used globally in time in many papers on dispersive equations. We we implement the loss of regularity in time. So we don't do a Newton scheme. We'll prove everything by bootstrap directly on the nonlinear equation. So the index of Gevrey regularity will decay slowly from an initial value to a final value. And a third thing, these are things which sort of improve the proof, but now we have prices to pay. In particular, the proof is more tight when we do the estimates because we don't have a scheme where we could lose a bit of regularity for when we pass from one step to the other. So because it's more tight, we perform a high-low norms kind of estimates on the full distribution. So this is an idea that is present in wave equations, for instance. There will be a high norm estimate that grows in time, not too bad, polynomially. A low norm estimate that is uniform in time. And in between, there is the norm we search on which we'll prove whatever we want.
High refers to high and what?
So to be very precise, there will be a norm that will have one more Sobolev weight, for instance, that will be higher, slightly higher. And there will be a low norm where we remove, let's say, 2 in Sobolev correction. That will be lower. So the high norm will be better for regularity but growing in time. The low norm will be worse for regularity but uniform in time. That is a sort of classical idea when you have this trade between regularity and time growth. And this is for the full distribution. So let's say these are the key elements of the proof.
You don't have any kind of Nash or Newton iteration scheme.
No,
Is that
I should emphasize that there is no Newton iteration in the end. That's what makes the proof less heavy.
but you have a continual loss of regularity. So
Yes.
Paraproducts.
So the
Kind of problem or what?
well, technical, it's more painful to write technically, but no, I would say no. Conceptually, it is not something that creates a lot of problem. So maybe, well, I could, since I don't have so much time, let me try to skip to a core aspect. Okay, what I will do, maybe I will just write the typical nonlinear equation in Fourier we will work on and explain the paraproduct aspect, which is probably one of the key things. How we replace all the aspect of linearizing in the Newton scheme by the paraproduct for distinguishing transport and reaction aspect. So we reframe the problem in the moving frame. So this is my fluctuation at time t, and I define a new unknown, g, to be depending on a new variable z, which is just x minus vt. So I'm really writing the evolution in the moving frame. I obtain an evolution on g which has this form. I will write 2 or 3 equations so that you have an idea of the equation. Won't have time to write everything, but okay, this is the background profile I'm perturbing. So this term is still here. So this is a linear term. The force depends on g, and this is my bilinear term here and in the force. And I pass everything in Fourier. So all the analysis is done on the Fourier side, which is also a reason for the limitation of going to more complicated geometry, global Fourier. And we get one equation for the full distribution, which has this form. So rho is the same rho as before. It's the rho associated with h. And I will try to use this equation on the blackboard to comment on the difficulties. Okay, this is my linear term, and then I have my nonlinear term. Okay, this is a bit confusing at first sight, but it really contains everything about how modes talk to each other. And you see already that a priori, if you see t in the coefficients, it's not a good sign for establishing estimate, but this is clearly fine because this multiplier is the same as here, so we can use the regularity of f0. But this clearly has a problem a priori. We don't have the same thing here and here. So that's the source of possible nonlinear instability. And we couple this system, let's call it 1, on the full distribution, even if it's closed in itself. But to perform estimates on rho, we couple that with a system on rho. So how do we get from that to rho? Observe that rho k at time t in Fourier is G Fourier mod k t kt. This is the origin of this kt everywhere. Right? So if we establish estimate in Gevrey here, this explains why we get the kt in the end for rho. And we have this second equation, which now is integral on rho. So you just project that on kt, integrate in time, and you get this equation. So that's my linear term again, d tau, and just write it here. And I have the nonlinear term also in the equation for rho, which is this term. Where now really modes interact. And we have tau and this complicated thing. Okay, so let's comment on these two systems. Again, we see the problems here. So what we will do is we study that as a coupled system. We have to establish both estimates on G and on rho. The hardest one to establish is on rho. If we have it on rho, then this term becomes less of a problem by plugging the good bound we have on rho. Okay, there are technicalities, but then it reports all the problems on controlling this term. Okay, this is the worst term here. The two linear terms, I won't speak much about them. They are treated by similar techniques that are used for proving the linear stability, using Fourier Laplace and so on. So let's skip that. And also, we see that this term is also worse because there is nothing like a transport structure with its cancellation. Rho here cannot be interpreted as being coefficient gradient rho, something like that. So at that point, for the questions before, there was a Newton scheme in what we were doing. So let me explain at a general level what we do to replace that. Let's imagine we have a product of two functions. By performing the Newton iteration, we linearize. So by linearizing, we will obtain G1 from previous step time G2 in this step plus G1 in new step, G2 in previous step, typically. And there will be the quadratic error term of G1, G2, both in previous steps. Right? That's the basic idea of the Newton scheme, of this iterated scheme. And the previous step will have more regularity. That's what we used in the scheme. That's what is used in results based on Nash-Moser. Here, by Littlewood-Paley and the Boni paraproduct decomposition, we write things like that. So we decompose this product in 3 terms. The first term is when G has a much lower frequency than G2. The second one is the symmetric one. And the last one is when they have approximately similar frequencies. So this term can be seen as an operator on G2 with coefficient from G1 in some sense. We can use that the coefficients are better here. This one is the symmetric again. And for this one, it plays a similar role as the bilinear remaining term in Newton iteration, because you can split evenly the regularity on both terms. So you get 1/2 on each, and so it's much better. Okay, so this one is easy. This is the easier one to treat. If now you think of G1 as being rho and G2 being F, basically, when you put low frequencies on rho, this is what will produce what we call transport. And if you put high on rho, this is what produces what we called reaction. So these names were in the paper with Cedric, but it's what's coming from a linearization argument. The bridge between the two things, and you know that there are several results that had first been proved by Nash-Moser that then were proved by paraproduct techniques or other techniques, but this one is known as being sometimes able to replace this Newton iteration. The bridge between the two things is that we are linearizing the evolution of higher frequencies around lower frequencies, of the highest regularity of the equation around the lower regularity of the equation. This is the bridge between the two things. In one case, it's higher because it's the next step of the scheme, and in this case, it's because of frequency decomposition.
Now, when the frequencies are comparable, like in the third term,
Yes.
why is that okay?
Well, basically, you will, in this kind of term, you will be able to split your multiplier regularity weight evenly between each of them. So it's like you have a multiplier. In one case, you put it most of it here. In the other case, you put most of it here. In the last case, you spread it. And if you spread it, of course, you get much below the level of regularity you're trying to estimate. Actually, and it turns out that those techniques are much easier to implement in Sobolev and Gevrey than analytic for once, but not impossible. But in Gevrey, the inequalities to implement what I've just said are very easy. To split the weight or put it on one side or on the other. Okay, so maybe, I don't know, how much time do I have? Okay, so okay, so I will stop on the another key idea. So the echoes estimate is absolutely crucial. However, the echoes estimate in this paper or refinement of the echoes estimate we had done with Cedric. There is no real conceptual big difference. So let me explain the second idea, high-low norms. So the kind of bootstrap we do in the end is the following. We have 3 estimates. Let's call one is high, low, and one is density that we propagate in time. Okay, so I've not defined all the names, so so let's say, let me try to make it shorter by doing that. So I put a weight in V, but you can forget that. We need the weight in V to be able to get the trace on the KT and so on. I have the full distribution. And then I estimate that in G, the lambda T and sigma plus 1 S, and some constant, some growth in time, and some epsilon. So actually we do that with squares. And the second estimate is again on the full distribution, but with sigma minus 2. And now it's uniform in time. And the last estimate, it's integral in time for technical reasons, because we work on the integral equation on rho. And it's in this F norm. Okay, so then we bootstrap these three estimates. Assuming taking the maximal time so that this is correct, this is satisfied, we prove that we can still extend this time. Okay, that's a kind of continuation argument. But, and all these a priori estimates are justified because there are already existing results about constructing smooth solutions to Vlasov-Poisson equation. The problem is to have these asymptotic controls. So if you forget about the weight in velocity, that's exactly what we want to prove. You have one estimate which is a bit higher, one estimate which is a bit lower. Here you have growth in time and so on. So when you want to bootstrap, you prove this one, and to prove this one, you use the paraproduct to decompose the bilinear terms that you see. So this one, you do paraproduct to decompose this rho and this F like that. The bilinear remainder is not hard, but you have to interpret one term as transport, one as reaction. For the transport term, you use the high norm here. But since it's low on rho, you have a lot of space of exponential decay, stretch exponential decay to kill the growth T to the 7. I'm just trying to give some typical things we do. On the reaction term, it's the hardest one. We need to perform this echoes analysis, very detailed, which is time decomposition, very detailed of the kernel to check that we can control things. And then we go back to the full distribution. Once we have the third control, we plug it to control, again, for the bilinear term, we split it like that. And for the transport term, we need to use commutator to check that the loss of one derivative, well, actually S derivative, sorry, is actually matched by the fact that since lambda is decreasing, it gives a bit of a negative term, a bit like in Cauchy-Kovalevskaya. You know, when you prove Cauchy-Kovalevskaya with a decreasing exponent of regularity, it gives a negative term in the energy estimates. And this term exactly balances the loss of derivative. And then you use that to control, in the bilinear term, to control it. But still, you have time growth because everything is at the highest level of regularity. And the low norm estimate, this one is performed a bit like that one, but it's simpler. Since you have some margin, you kill the time growth. Okay, but in spirit is the same. So you have to prove them in the right order, decomposing things like that. And the decomposition is not hard. I mean, you do Littlewood-Paley, and this one means like this is 8 times less than that, 8 times less than that, and this one means the frequencies here are between 8 times and 1/8 the other. This is just what it means in Littlewood-Paley. So okay, I will stop here. Thank you very much.